When you think about stepping into a hospital or just looking at a clinical diagnosis, there is this deep expectation of, absolute precision.
Right. Yeah. Like zero room for error.
Exactly. You break your arm, the X-ray shows that jagged white line, and the doctor points to the film and tells you exactly what is wrong. It's visible, it's measurable, and like highly concrete.
Which is deeply comforting, I think. We really rely on that visible certainty, especially when patient safety and, well, human lives are on the line. Medical science is fundamentally built on the idea of removing ambiguity.
And here's the crazy part. If you take a step back and look at the ultimate gatekeeper to working in that hospital, specifically for anyone trying to pass the TEAS or HESI nursing entrance exams, that concrete precision just kind of vanishes.
It really does.
Suddenly you aren't looking at an X-ray anymore. You are looking at a diagnostic landscape that is entirely abstract. Because the ultimate gatekeeper to saving lives is the letter X.
Oh, the ghost of K-12 math trauma path. I mean, it is the absolute definition of a conceptual hurdle. For someone who wants to deal in the physical reality of patient care, stepping into the abstract mud of algebra feels deeply, deeply counterintuitive.
So whether you are actively sweating over those nursing exams right now or, you just want to understand the hidden logic of the world around you, we're going to do a deep dive today into the mechanics of solving for X.
Because the way K-12 textbooks present this topic usually strips away all the magic.
Yeah, completely. To actually master this, you have to understand its 3,800-year history, the literal life and death stakes of getting it right in a clinical setting, and the cognitive tricks required to decode it.
Which is a lot to unpack.
It is. Yeah. So let's unpack this. And to do that, we have to start by asking why the letter X even exists in the first place. Because for the vast majority of human history, it just didn't.
No, it didn't. And the origin of the discipline itself is actually completely unexpected. The word algebra is fundamentally a medical term.
See, that blew my mind when I read the source material. A math discipline universally feared by nursing students actually shares its DNA with the medical field.
It's wild, right? It comes from the Arabic word aljabr, which roughly translates to the reunion of broken parts or like simply restoration.
Oh, wow.
Historically, in the Middle East and medieval Europe, that exact root word was the formal medical term used for the practice of bone setting.
Taking broken, disjointed pieces and applying a systematic, careful process to restore balance and wholeness, which is, exactly what a nurse does, and structurally, exactly what an algebraic equation is doing.
Exactly. And the mathematical version of algebra was formalized in the 9th century. There was a Persian scholar named Muhammad ibn Musa al-Khwarizmi, and he wrote a foundational text while working in Baghdad's House of Wisdom around 820 CE.
So right in the middle of this intellectual golden age.
Right. Scholars were gathering knowledge from Greece to India, but al-Khwarizmi wasn't trying to invent abstract puzzles just to torture future generations of students.
Thank goodness.
Yeah, he was actually building a highly practical toolkit for everyday problems.
Right, because he was dealing with 9th century real-world headaches. Like he needed a way to calculate complex Islamic inheritance laws, which required dividing estates among dozens of heirs according to very strict, fixed fractions.
Yes, and merchants needed to calculate trade deficits, and surveyors needed to measure irregular plots of land. It was very hands-on.
So to solve those problems, his book systematized 2 specific operations, right?
Yeah, so the first was algebra restoration, which basically meant moving a subtracted or negative term to the other side of an equation to make it positive.
Okay, that makes sense.
And the second was al-muqabala balancing, which meant combining terms on each side to simplify the problem.
And as an incredible piece of historical trivia, when al-Khwarizmi's own name was translated into Latin centuries later, it actually gave the modern world the word algorithm.
Which is amazing. I mean, his influence is embedded in almost everything we do mathematically today. But if we look at how he actually wrote his equations down, we hit a massive evolutionary bottleneck in human communication.
Right, because he didn't use the letter X.
No.
He didn't use an equal sign either, right? None of the modern symbols we use to do math existed. He wrote everything out in prose.
Yeah, historians break the evolution of mathematical notation into 3 distinct phases. And the first is rhetorical algebra.
Rhetorical meaning just words.
Exactly. This is what Babylonian scribes were doing on clay tablets as early as 1800 BCE, and it is what al-Khwarizmi was doing in Baghdad. It was entirely rhetorical, meaning it was written out in full, exhausting sentences.
Oh my gosh. Imagine trying to pass a nursing exam, but instead of reading a short equation, you have to read a paragraph that says, the thing when multiplied by itself and added to 10 times the thing, results in the quantity of 39.
It sounds like a riddle.
It does. It's a massive cognitive load just to hold the sentence in your working memory, let alone actually solve it.
Which is exactly why the second phase became inevitable, which is syncopated algebra. So around 250 CE, an Alexandrian mathematician named Diophantus started using abbreviations for recurring quantities and operations.
Kind of like how we use shorthand in text messages today to save keystrokes.
That's a perfect comparison. Diophantus is heavily debated as the quote-unquote father of algebra for this, though many scholars point out he was mostly solving one-off numerical puzzles, whereas Al-Khwarizmi taught general, repeatable systems.
Okay, so phase 1 is writing a dense novel, phase 2 is texting shorthand, and phase 3 is the symbolic algebra we use today.
Right.
And what I love is that the people who invented those modern symbols did it purely out of frustration. My absolute favorite from the sources is Robert Ruckord.
Oh, the Welsh mathematician.
Yes. In 1557, this guy was writing a textbook, and he just got fed up with writing the words is equal to over and over again. So he just invented the equal sign. He drew two parallel horizontal lines because, in his own words, no two things can be more equal.
I love that. It is the ultimate triumph of pragmatism, and the standardization of those symbols just continued from there. In 1591, the French mathematician François Viet started using letters to represent both known and unknown quantities.
But it was René Descartes in 1637 who finalized the visual landscape we recognize today, right?
Yes, Descartes decided that letters from the beginning of the alphabet A, B, and C would represent known numbers, and letters from the end of the alphabet X, Y, and Z would represent the unknowns.
So we literally only solve for X instead of like Q or M.
Yeah.
Because a French philosopher made a typesetting choice for his publisher.
Exactly. And what's fascinating here is that there's a linguistic theory about why Descartes might have leaned toward the letter X in the first place.
Right, the Arabic connection.
Yeah, the Arabic word used by scholars for the thing or the unknown was al-shay.
But translating Arabic into medieval Spanish created a massive phonetic bottleneck. Spanish monks and translators couldn't pronounce the sound in al-shay.
Right, the sound didn't really exist in their language in the same way.
So they substituted the shesh sound with the classical Spanish letter X, spelling it say. And over time, European translators simply dropped the rest of the word, leaving the single letter X to stand in for the unknown thing.
It's incredible. When you look at that 300-year timeline, you realize that solving for X isn't some timeless, fixed law of the universe. It's just the modern endpoint of human beings desperately trying to compress complex verbal reasoning into a portable, highly efficient symbolic language.
Okay, so symbols compress language and save time. But, if you were sitting in a testing center sweating over an equation, historical trivia doesn't actually help you isolate the variable.
Fair point. You have to manipulate that compressed language.
Right, you need a mechanical strategy. So the best way, I think, to look at isolating a variable is to imagine a heavily wrapped gift.
Okay, I really like this analogy. Let's trace the logic.
Imagine I put a gift, the X, inside a box. I tape the box shut, I wrap it in paper, and I tie a tight bow around the whole thing. If you want to get to the gift, you can't just smash the box open.
Obviously not.
You have to take the packaging off in the exact reverse order that I put it on. You have to untie the bow first, then tear off the paper, cut the tape, and finally open the box.
Right, and in formal mathematical terms, this unboxing process relies entirely on the balance scale concept.
The balance scale.
Yeah, at its absolute foundation, an equation is a physical scale. Whatever sits on the left pan must weigh exactly what sits on the right pan.
Makes sense.
Isolating X means you are allowed to add, subtract, multiply, or divide. But if you do something to the left pan, you must do the exact same thing to the right pan simultaneously. If the scale tips, the math fails.
Which highlights one of the most common fundamental hurdles for anyone relearning math for these nursing exams.
Mm-hmm.
People are conditioned to treat the equal sign as a command prompt.
Oh, absolutely. The cognitive conditioning starts in, first grade. You learn basic arithmetic, 2 + 3 = 5. You read left to right, you perform a calculation, you hit the equal sign, and you produce an answer.
It feels like an action button on a calculator. Like, here comes the answer.
Exactly. But an algebraic equation is not a one-sided instruction. The equal sign is a statement of perfect equilibrium. It tells you that the left side and the right side represent the exact same quantity, just wearing different clothes.
Right, because it's a balance. You can perform operations on the quote-unquote answer side, too. It's not a finish line, it's a pivot point.
And this is where your unboxing analogy becomes the mechanical engine for solving the problem. To untie the bow and rip off the wrapping paper, you use reverse PEMDAS.
PEMDAS being the standard order of operations, right?
Mhm.
Parentheses, exponents, multiplication and division, addition and subtraction.
Right. When you evaluate an expression, you go in that order. But when you want to isolate a variable, you peel those operations off in the opposite direction.
So you target the weakest bonds first.
Yes. You undo the addition and subtraction, because those are loosely attached to the x. Then you undo the multiplication and division, which are more tightly bound to the variable.
Okay, let's visualize this without getting bogged down in heavy numbers. Imagine an equation that says 3 times x plus 5 equals 20.
Okay, so using reverse PEMDAS, we look for addition or subtraction first. We see a plus 5.
Right.
To remove that layer of wrapping paper, we apply the inverse operation, which is subtraction. But to maintain the balance scale, we subtract 5 from both sides. 20 minus 5 leaves us with 15 on the right side.
Now, the scale reads 3 times x equals 15. The addition is gone. We move to the next layer, which is multiplication.
Right.
The x is being multiplied by a coefficient of 3. So to untie that knot, we divide by 3, and we do it to both sides. 15 divided by 3 is 5. So x equals 5.
And the logic holds perfectly even when the visual presentation looks terrifying. Like if a student sees fractions say x divided by 4 minus 3 equals 9, the brain often just panics.
Well, yeah, fractions induce immediate math anxiety. But if you trust the unboxing process, it's just as simple. You handle the loose bonds first, the minus 3.
Yep.
The inverse is adding 3 to both sides. 9 plus 3 is 12.
Now your scale is simplified x divided by 4 equals 12. To undo division, you multiply. You multiply both sides by 4. 12 times 4 is 48. The variable is isolated.
Okay, so this brings us to a massive underlying question. Why does the medical field care if you can unbox a variable? Like, nurses are not sitting in hospital break rooms drawing algebraic proofs on napkins.
True.
Why is abstract math the gatekeeper?
Because the hospital floor is an environment of high stakes and high chaos, and cognitive slips in math cause catastrophic harm.
Wow.
Nursing and pharmacy safety literature consistently identifies calculation mistakes as a primary source of entirely preventable medication errors.
Literally the difference between a patient recovering and a patient going into cardiac arrest.
Exactly. Let's map this to a clinical scenario from the sources. A nurse is looking at a vial of medication. The label says there are 250 milligrams of the drug suspended in every 5 milliliters of liquid.
Okay.
But the physician's order calls for a 400 milligram dose. The nurse has to figure out exactly how many milliliters of liquid to draw into the syringe.
This requires setting up a proportion. And a proportion is just an equation stating that two ratios are perfectly equal. So 250 milligrams over 5 milliliters equals 400 milligrams over X milliliters.
Right. To solve a proportion, you rely on a mathematical shortcut called cross-multiplication. You multiply the top of one side by the bottom of the other. So 250 times x equals 5 times 400.
Okay, and 5 times 400 is 2,000.
Which leaves us with 250 times x equals 2,000. And look at that, we are right back to the basic balance scale.
Yep, unboxing the variable again. We divide both sides by 250. 2,000 divided by 250 is 8. So the nurse needs to administer 8 milliliters.
See, the clinical scenario is just the balance scale wearing scrubs. But this high-stakes reality reveals the core tension in a massive, decades-long debate in K-12 education, which is widely known as the math wars.
Oh, the battle over how human beings actually learn this stuff.
Exactly. If we connect this to the bigger picture, this conflict really ignited in 1989 when the National Council of Teachers of Mathematics released a new set of standards, and the education world sort of fractured into two camps. One side argued heavily for procedural fluency. This means teaching students to memorize the steps, like the cross-multiplication recipe we just used, until it becomes automatic, low-effort cognitive instinct.
Which, to be fair, our brains love procedural fluency. It's the same cognitive pathway as riding a bike or driving a car. You don't have to think about the physics of balance to ride a bike, you just pedal. If you just memorize the math recipe, it requires very little working memory.
But the rival camp argued for conceptual understanding first. They believed that teaching the deep logic of the balance scale had to precede the procedural drills.
Why is that?
Well, their argument was that procedural memory is fragile in novel situations. If a student only knows the steps but doesn't understand why the scale balances, the moment a word problem is phrased strangely, their rigid recipe fails and they panic.
Which is so interesting. Now, obviously, both sides of the K-12 curriculum debate have incredibly valid points about human development, and we're definitely not picking sides on how third graders should learn math.
Oh, for sure.
But when we look specifically at the clinical environment of nursing, the safety literature takes a really definitive stance. A lack of conceptual understanding is what actually leads to dangerous hospital errors.
Because a hospital floor is not a quiet classroom. Alarms are ringing, patients are coding, nurses are working 12-hour shifts and suffering from severe cognitive depletion.
Oh, completely exhausted.
Yeah, so if you only have a memorized procedure and you are exhausted, you might set up that proportion backward. You might put the milligrams on top on the left, but on the bottom on the right.
And if you don't have the conceptual understanding of the balance scale to, double-check your logic, you follow the flawed recipe to the end and you administer a clinically dangerous dose.
And that's why the nursing entrance exams are designed as a screening mechanism. They want to catch that exact failure mode in a quiet testing center long before it happens in a chaotic ICU.
Since getting this wrong carries such immense weight, it's vital to look at the cognitive traps that routinely sabotage test takers.
Let's do it.
But before we get to the modern traps, I has to mention how Al-Khwarizmi avoided them in the 9th century. He had a famous equation that today we would write as x squared plus 10x equals 39.
Right, a classic quadratic equation.
Because he didn't have symbols to push around a balance scale, he solved it visually. He literally drew a physical square in the dirt to represent x squared.
Wow.
Yeah, and he drew rectangles attached to the sides to represent the 10x. And then he figured out the exact dimensions needed to fill in the missing corners. He quite literally completed the square using actual physical geometry to find the value of x.
That is a beautiful reminder that solving for x began as a highly tangible geometric reality before it was ever compressed into symbols.
It's so cool.
But modern test takers don't have the luxury of drawing shapes in the dirt. They have to navigate the abstract rules, which leads to several well-documented cognitive pitfalls.
Like the trap of inequalities. This destroys exam scores. Imagine an inequality that says negative 2 times x is greater than 8.
Right, so the instinct is to treat this exactly like a static equation. You want to isolate x, so you divide both sides by -2. 8 divided by -2 is -4, so the brain assumes x is greater than -4.
And the entire solution set is completely wrong.
Because inequalities are not static balances, they represent directional thresholds. When you multiply or divide an inequality by a negative number, you are fundamentally reversing the direction of the relationship on the number line.
Oh, right.
You must flip the inequality sign. The correct answer is x is less than -4.
Our brains are just so deeply trained by the static nature of the equal sign that we forget to account for the directional shift. It's a massive blind spot. What about subtracting negatives? That's another huge stumbling block.
Oh yeah, it comes down to linguistic confusion. If an expression reads x minus -4, the double negative basically overloads our working memory.
It's like saying, I am not opposed to not going. You have to pause and translate it.
Exactly. Mathematically, subtracting a negative debt is the exact same thing as adding a positive asset. X minus -4 is simply x plus 4. Failing to make that simple translation early in a problem guarantees the final answer will be wrong.
Another subtle trap is assuming that math only ever yields one clean, positive answer.
We crave simplicity, but equations are perfectly happy to yield negative numbers, fractions, or even infinite solutions. In more complex algebra, you often encounter extraneous solutions answers you arrive at through perfectly legal algebraic moves, but when you test them in the real world of the original problem, they break the logic.
Which brings us to the ultimate failsafe, the golden rule of algebra. You are never ever done until you plug your final answer back into the original equation to prove it works.
It is the only reliable defense mechanism against human error.
If you do the math and determine x equals 5, take the 5, drop it back into the raw, untouched equation, and make sure the left side actually equals the right side. It takes 5 seconds. In a hospital, it saves a life. On an entrance exam, it secures your passing score.
It forces you to switch from procedural memory back to conceptual reasoning, closing the loop on the problem.
Okay, let's pull all of this together for anyone preparing to face down these exams. First, treat every equation as a physical balance scale. Whatever you do to one side, you must replicate on the other.
Check.
Second, use reverse PEMDAS to unbox the variable, stripping away loose addition and subtraction before tight multiplication and division. Third, retrain your brain to see the equal sign as a statement of equilibrium, not a command to calculate.
Very important.
Fourth, Always verify your work by plugging the answer back in. And finally, when dealing with clinical dosage or dilutions, set up a proportion and cross-multiply. It's the exact same balance scale logic applied to patient care.
And it is worth recognizing that you use this logic far beyond the walls of a hospital. You use algebraic reasoning to calculate a tip, to compare the interest rates on 2 different car loans, to figure out how many gallons of paint will cover a living room, or, to scale up a baking recipe for a larger dinner party. You are constantly balancing the scale.
Which leaves a fascinating question to consider for you, the listener. We learned today that algebraic notation evolved over 3,800 years, from Babylonian prose on clay tablets, to Theophantus's shorthand, to Descartes standardizing the X, all to compress human reasoning to a faster, more efficient visual tool.
Right.
As technology and computing continue to advance at an exponential rate today, what might the next evolution of mathematical notation look like for future generations? Will the letter X and the parallel lines of the equal sign someday seem as archaic and clunky to them as reading a Babylonian paragraph seems to us?
Will we interface with math visually? Will AI translate our spoken logic directly into structural models without the need for symbols at all? It is a profound shift in how humans might communicate logic.
It really is. So the next time you're staring down an abstract math problem, searching for a clean, visible answer, remember that you aren't just pushing letters around a page. You are participating in a 3,800-year human tradition of taking broken, disjointed pieces and applying a rigorous system to make them whole again. Thank you so much for joining us on this deep dive.